So, famous quote attributed to Albert Einstein, but I think we're not really 100% sure that he said it, which is why I wrote attributed to and not just Albert Einstein, is that the most powerful force in the universe is compound interest. So last class we talked about simple interest. And with simple interest, only the principal, only your initial investment generates interest. But under compound interest, not only does your principal, not only does your initial investment generate interest, but so does previously accumulated interest, right? So not only your initial, let's say $1,000 gains interest, but your $1,000, let's say you make 10% interest in a year. So the next year you have $1,100 because you made 10% interest. The next year you make 10% interest on $1,100, not just on the initial 1,000. So with compound interest, your interest earns interest. Money invested using compound interest grows much faster than money invested under simple interest. So example, imagine that your parents invested $5,000 at a 6% APR. And APR, remember, stands for annual percentage rate. That's how we generally express interest rates on the day you were born. So we want to figure out how much the investment is worth 1 year later, 2 years later, 3 years later, 4 years later, and T years later. And we're going to earn compound interest. So interest earns interest. So I'm going to make a little table, and I'll put time and amount. Okay, so at time 0, right, the day you were born, we'll call that time 0. The amount in this, the value of this investment is $5,000. One year later, that $5,000 will have earned 6% interest. So I'm going to get a calculator out here. So if I want to increase 5,000 by 6%, how do I do that? So close. 1.06 times 5,000. Why 1.06? Because you keep 100% of your $5,000 and you add an additional 6%. So if I multiply 5,000 by 1.06, we get $5,300. So 1 year later, that investment is worth $5,300. All right, now I want to increase 5,300 by 6%. Okay, so I'm going to take my 5,300 and multiply that by 1.06. And I get $5,618. So you see, it's not growing by the same amount each year. From year 0 to year 1, we earned $300. And from year 1 to year 2, we earned $318. So the more money you have in the bank, the more interest you earn. Right? All right, so for year 3, I'm going to take 5,618 and multiply that by 1.06 to increase that amount by 6%. And in year 3, we have 5,955.08. We'll do one more year. Year 4, we multiply times 1.06, and we get 6,312 and 38 cents. All right, what if I want to write a general formula? I could think of this as a sequence, right? This is a sequence of the amount in my bank account at the end of each year. What if I want to write a formula for that? Saying I could do it, because what kind of sequence is this? Exponential, yeah. Because we're always multiplying by the same amount, right? we're multiplying times 1.06 times 1.06. And when you always multiply by the same amount, that's exponential growth. So you have an exponential growth here, and we know how to write a formula for exponential growth, right? Take your starting amount, 5,000, and to get from year to year, you're always multiplying by 1.06, and you would have to multiply by 1.06 t times for however many years have passed, so you do 2 to the t. So there's my formula for the amount of money in that bank account after t years. That make sense? Everybody good? Okay. So now I'm going to use that formula to fill in this table where my numbers are much bigger. 10 years, 20 years, 30 years later, how much money is in that bank account? So I guess I closed my calculator. So I need my scientific view. 1.06 raised to the 10, and then multiply that by 5,000. So that's how much is in the account after 10 years. 8,954. And I'm just going to round to the nearest dollar. Obviously, a bank would round to the nearest penny, but just for space reasons, so I have room to write all my numbers. All right, year 0, right, I know that's 5,000. That's how much was in there at the very beginning. All right, let's look at 20 years later. So I do 5,000 times 1.06 raised to the 20th. And I have $16,036. So the money has more than tripled in 20 years. All right, let's look at 30 years. 5,000 times 1.06 raised to the 30th. 28,717. Round to the nearest dollar. And then I'll do 40 years. 50 times 1.06 the 40th. Oops, messed something up. 5,000 times 1.06 raised to the 40th. 51,428. I guess if I'm rounding correctly, that would be 29. All right, and then 50 years and 60 years. 5,000 times 1.06 raised to the 50th. $92,100, $101. And after 60 years, we have $164,938. So you can start to see why Albert Einstein called this the most powerful force in the universe, right? Start with a small investment of $5,000, and if you let it grow at a pretty modest 6% growth rate for 60 years, you end up with almost $165,000. Imagine what it would become if you added to it yearly. We'll talk about that in another class. All right, so I always want to plot these points on the grid. I have on the horizontal axis, this is going to be time, and the vertical axis is the amount of money in the bank. So I have 0, 5,000, starts way down here. And then 10 was almost 9,000. So these are very rough because the grid is not fine enough to go to the dollar. So just roughly place these points there. Okay, 20 years is $16,000. So that's 20,000, so that's about right there. And 30 years, we have about 28,000, somewhere around there. And then 40 is 51,000. Right, a little bit bigger than 50. And 50 years, we have 92,000. So I'm at almost 100,000. And then after 60 years, I have about 165,000. A little bit off the grid. So you can see the size of the jumps from year to year gets bigger and bigger and bigger. Right? So my jump from year 0 to year 1 is relatively small. It's just a teeny tiny little jump, right? And then the vertical distance from year 1 to year 2 is a little bit bigger, and then it gets even bigger, and then it gets even bigger and bigger and bigger. So we have this curve that looks like this, and that's generally what exponential growth looks like. It's this curve that shoots up really fast. All right, so let's try to get a general formula for annual compounding. So I'm going to take the formula that we wrote earlier, this 5,000 times 1.06 to the t, and I'm going to try to generalize it to a random principal amount and a random interest rate. Okay, so I'm going to replace my 5,000 with a generic principal amount P and change the 0.06 to a generic interest rate R, and the future value of P dollars invested annually for T years at an APR of R%. Future value is equal to P for, you can think of that as principal or present value, times, instead of 1.06, I'm going to have 1 plus whatever my interest rate is. It'd be like 1 point R when you add them together, to the T. All right, so let's use this formula for a problem. You have $875 in savings. You want to invest it so it will grow. And your goal is to have $2,000 saved in 7.5 years. So your local bank is offering a CD that pays a rate of 6.75% annually. What is the future value of your $875 in 7.5 years? And if you're short of your $2,000 target, how much more will you need to invest to meet the target? All right, see if you can discuss in your groups and figure this one out. Okay, ready? So you have $875, you're going to invest it for 7.5 years at 6.75% compounded annually. All right, so I'm going to write down my formula. Future value is present value times 1 plus R to the T. Okay, now I'm hoping that my future value is $2,000, but that's not a given, right? That's not one of the things that I know for sure. I'm hoping this comes out to $2,000. Okay, so if you want to put in everything that you're given, you could write, does this equal 2,000? Little question mark. If your principal, your investment is 875, you always have to change your interest rate to a decimal. So 6.75% as a decimal is 0.0675. Now here's a little trick. Pretty much everyone put a 7.5 here. But when you're compounding annually, that means once a year. Like December 31st, you get paid your interest. So if you take your money out in June, you don't get your interest for that year. Okay, so we actually are only going to have this money invested for 7 years. Yeah, I know. Are you trying to keep us on our toes? Trying to keep you on your toes, yes. So no, I'm leading up to something. Okay, I'm leading up to something. So yeah, if you put your money in an account that only pays interest once per year, you only get your interest once per year. And if you take it out before that date where they pay the interest, you don't get that year's interest.
So the 7.5, it's the 0.5 years kind of red herring.
Yes, red herring. Yeah. And in the next problem, we're going to find a bank that will pay us for that half a year. Okay. So
whenever we see that, should we be worried, or
if it says annual,
annual?
yeah. Yeah. Okay, so let's see how much is in there after 7 years. Okay, so I have to just be careful to follow the order of operations, which says you should always do what's in parentheses first. So I add 1 plus 0.0675, and I get 1.0675. Then I do the exponent, so I'm going to raise that to the 7th, and then I'm going to multiply by 875. And I get, does not equal $1,382.23. Why did I round that down? Shouldn't it be rounded to 24 cents? Not in corporate America, right? No, the bank's never going to give you your extra piece of a penny. Right? It'll always round it down. Has anybody seen Office Space? That's like the whole scheme where they take the pieces of a penny that the bank refuses to give you and they collect it all and they have this bank account that grows ginormous. Yeah. All right, so we don't have enough. We have not met our goal of $2,000. So now I have to figure out how much do I have to invest? I want to change this 875 number. How much do I have to put in to make sure I have $2,000? So now I'm going to put in 2,000 for my future value. I'm going to leave P a variable or an unknown to solve for. 1.0675 raised to the 7th. And now I'm going to solve for P. So I'll just simplify that 1.0675 to the 7th. I saw some people solving this by trial and error, which is totally fine. Raised to the 7th, and I get 2,000 is 1.579702. That's probably good enough. P. As a general rule, you shouldn't round things until the very end of a problem, especially when it deals with money, because the rounding errors can compound and get bigger and bigger as the problem goes on. So at least keep like 5 or 6 decimal places. Or you can use the store function on your calculator. So I can store this number on this particular calculator, I press M+ for add to memory. You guys all have all of your calculators have a different way of doing it. Like this one, there's STO with a little arrow, and you can store it as a letter in most of the scientific calculators. I'll come around and show you individually because you all have a different calculator. So, all right, so now when I clear this, that number is still stored in my calculator's memory, and I can tell because there's a little M here. Something's in the memory. All right, so to solve for P, I want to divide by this number, 1.579702. So my P is going to be 2,000 divided by, I could just type in that number because I wrote down a bunch of decimals, so I should be okay. Or I could recall the number that I stored. On this particular calculator, you press MR for memory recall. And then hit equals, and I get $1,266.06. So that's how much I would need to put in today in order to have 2,000 7 years from now. Okay? All right, so we're going to do another example. It's the same scenario as above, except this bank is offering to pay you part of your yearly interest each month. Okay, so instead of paying you your 6.75% in one big chunk at the end of the year, they're going to pay you a little bit of it every month. So you're getting more money sooner, so you should earn more interest because interest earns interest, right? Plus, you're going to make interest on the half year that you didn't get anything for before. So now we can actually plug in 7.5 years, not 7. All right, so if my interest rate, R, is 0.0675, we have something called a periodic interest rate. So they're going to pay us interest 12 times a year, right? We're going to get our interest paid monthly. So if I'm going to get 12 times per year, the interest rate I'm going to get is actually R divided by 12. They're going to take my yearly interest rate and break it up into 12 equal payments. Well, not equal payments, 12 interest rates. So I take my 0.0675 and divide by 12, and I get 0.005625. This is already a decimal, right? Because I started with a decimal. This is already a decimal. So I don't need to move my decimal point at all. All right, so let's say my future value is going to be my present value of 875 times 1 plus 0.005625. Okay, but how many times are they going to pay me this over 7.5 years? 90 times. Because they're going to pay me monthly, right? So 7.5 times 12. So they're going to pay me this interest rate 90 times over the course of this investment. So I raise that to the 90th. Does that make sense? So my interest rate is smaller now because I'm getting paid it monthly, but I get paid 90 times instead of 7 times or 7.5 times. All right, so I put this all in my calculator. Parentheses first, so I add 1 plus 0.005625. Then exponent, so I raise that to the 90th. And then times 875. And I get $1,449.61. So I still don't reach my $2,000, but I am closer than I was with the previous investment. Okay, I made a decent amount more money. All right, what if we compound daily? What if I take that 6.75% interest rate and I pay you a little bit of it every day? You don't want to. So I take my R, which is 0.0675, and I have to divide it by what? 365 days in a year. So 0.0675 divided by 365 that's a really small number. That e to the -4 means move the decimal place 4 to the left. So this is 0.1231849. 315. I want to be really accurate. So that is my daily interest rate. My periodic interest rate is my daily interest rate in this case, which is 0.0001849,315. As a percent, that's 0.018%. This is already a decimal. All right, so my future value is going to be my present value of 875 times 1 plus that number, 0.0001849,315. And how many times am I going to be paid interest over 7.5 years? That's in 1 year I get paid 365 times. We can ignore leap years. Yeah, so I have to multiply 7.5 years times 365 days in a year and I get paid my small interest rate 2,737.5 times. Oh yeah, they might not pay you for the half day. We'll just ignore that for now. A half day I don't think is going to make any difference. Okay, so order of operations, oh shoot, 0.0675 divided by 365. I'm going to store this number, m plus, clear, and then I have to do 1 plus that number. All right, and then I have to raise that to the 2,737.5 times 875, and I get $1,451.60. Then you made a mistake. So how much more money did I make compounding daily as opposed to monthly? About $2, right? $2.01. Yeah. Actually, $1.99. What? Here? The number on my calculator was 1,451.607. You always round down to the, you don't round to the nearest penny, you round to the penny below. At least when the bank is paying you, you round to the penny below. When you're paying the bank, you probably round to the penny up, right? On loans and stuff, they want to make sure they get everything that they're owed. So you would round up. Yes, we made $1.99 more by compounding daily as opposed to monthly. This is our general compounding formula. The future value of P dollars in T years at an interest rate of R%. And R% we write, that's the same thing as R. Little r is the decimal, big R is the percent. N times per year. So the thing we followed up here is we always took R and divided by the number of compoundings. That's this R over N. And you have to do 1 plus that. And this is the total number of compoundings over the length of the investment. So we did 365 times 7.5, or 12 times 7.5. So this is the formula that we have been following. It's just all written out formally now. Same thing. All right, so I want you to try these three. What if you compound twice a day? What if you compound hourly? What if you compound every minute? How much will be in the bank account after 7.5 years? All right, let's do these together. I know that many of you are not completely done, but we need to also move on. Okay, so what if we compound twice a day, right? Then our interest rate, so I'm just going to write down my formula. Future value is present value times 1 plus R over N to the NT. N is the number of times you compound per year. T is the length of your investment in years. P is your principal, and R is your interest rate. So I have 875 times 1 plus, my interest rate is 0.0675 divided by, how many times am I compounding? 730. If I do twice a day, that's 365 times 2 is 730. And then I'm going to raise that to the N times T. N is my number of compoundings per year. So I would do 730 times T, which is 7.5. So that's 5,475. Does that make sense? Just plugging all that stuff in. Now this is the tricky part, right? Now I have to carefully follow the order of operations and never round anything. There's more than one way to approach this using your calculator. You can use a memory button, or you can just never clear anything. If you enter it carefully, you can never press clear, and your calculator will carry all the decimals. So what I'm going to do here is follow the order of operations. So if I'm going to do what's in parentheses first, the first thing in those parentheses is the division. So I would do 0.0675 divided by 730. And then I'm just not going to clear this number. Instead of writing it down, clearing it and retyping it, just leave it there and use it. So you just hit +1. And you get 1.00009246.5. Right? Okay, so then the next thing in my order of operations is to take the result from this parentheses, which is now written here on my calculator, and raise it to the 5,475. And I get 1.659. My next step would be to multiply all of that by 875. So I get $1,451.64. The key to coming up with that number is to never round. Okay. All right, let's talk about what would happen if we compounded every hour. So my future value is going to be my principal times 1 plus 0.0675 divided by my number of compoundings per year. So if I do hourly, how many hours are in a year? Well, there's 24 in a day times 365 in a year, 8,760. So if I compounded hourly, that would be 8,760 times in a year. And then I have to raise all of that to that number, the number of compoundings in a year, times 7.5 years. 65,700. All right, so I type this all in very carefully, following the order of operations and never clearing anything. If you come to a situation where you have to clear because you didn't think ahead, you can store the number, right, and call it back later. So I'm going to start with my 0.0675 divided by 8,760. Then I add 1 to that. Then I raise that to the 65,700. And then I multiply times 875. 1451.67. Okay, so I made 3 extra cents for my previous compounding. All right, and if I compound every minute, future value is my present value of 875 times 1 plus 0.0675. And I have to put how many minutes there are in a year, right? If I get paid every minute, I have to know how many there are in a year. So I would say 60 minutes in an hour times 24 hours in a day times 365 days in a year, and we get 525,600. All right, and then I have to take that 525,600 and multiply by 7.5 years to get the total number of times I'm going to be paid. 394,000, 3,942,000. All right, so now I'm going to carefully type this all in. 0.0675 divided by 525,600. Add 1. Raised to the 3,942,000 times 875. 14,051.67. Because remember, we always round to the penny below. So we didn't make any additional money. I mean, technically we made a partial cent more, but the bank takes that away. Yeah. So in practice, we didn't make any more money. So you can see compounding makes a big difference at first, right? So when we only compounded once a year, we made $1,266. About we came out, our bank account was worth $1,266. When we compounded monthly, that was a big jump to $1,449. Right? And then when we jumped to daily instead of monthly, we made an extra $1.99, $14.51.60. And then when we jumped from daily to twice daily, we made 4 cents. 3 cents. We made 3 cents. 4 cents. I don't remember what the one was before. And then we made 3 cents, and then we made nothing by adding more compoundings. And this is one of the remarkable properties of compound interest. Even as you let the number of compoundings increase without bound, right? If you just compound more and more and more frequently, we could have done every second. We could have done twice every second, right? Even as you let that number of compoundings go up, the future value approaches a limiting value. Even if the money were compounded 1 billion times per second, the future value would still not be more than this limiting value. And the limiting value represents the future value of an investment under continuous compounding. Continuous compounding means an infinite number of compoundings each year. So you're compounding like at every single moment, you're compounding interest. And it has its own special formula, P e to the RT. And E is a magical mathematical number, kind of like pi, kind of like the golden ratio. It goes on forever and ever, no repeating decimals. And it's approximately 2.71828. Has lots of applications in finance. The first one that we'll see being compound interest, continuous compounding. So the derivation of this magical appearance of E requires some calculus. So we're just going to accept it on faith for now. Just going to say, okay, that's the formula I use. If you see the words continuous compounding in a problem, you use this formula. Okay. So for example, let's figure out how much we would have if we invested $875 at an APR of 6.75%. And this time we're going to compound it continuously, right? Instead of telling you once a year or monthly or twice daily or every minute, I'm just going to say continuously. An infinite number of compoundings per year. Continuously, you use this formula. So I'm going to take my 875, multiply it by the number E to the 0.0675, that's my interest rate R, times T 7.5. All right, so on your calculator, you should have a button for E. So where's mine? Nope, that's not it. It's always lowercase, yeah. So maybe I don't have one on here. I guess I could just type in 2.71828, but that's a rounded number. It is already. I have a graphing calculator up here also. Okay, hold on. I will come around and find everyone's E calculator. Let's just finish the problem first. So you can type this problem directly in, so you don't have to do it a piece at a time. I can do 875 times. If you have a graphing calculator, your E button is 3 up on the left-hand column, and it's a second function. So you do second e to the x, and E is so often raised to a power that it automatically pops up with the little caret. What do you want to raise me to? Right? There's also a regular E, yeah, but I use this one. All right, and then you type in 0.0675 times 7.5, and we get $1,451.67. That's our limiting value. So even if we continued to increase our number of compoundings like we were doing before, we would never get higher than this. All right, I'll come around and help you with your individual calculators. Okay, so the annual percentage yield. So APR is the number that banks will often advertise, right? But APY is the best way to compare to interest rates. Because if one bank pays 6.75% compounded annually, and another bank pays 6.75% compounded continuously, the actual amount of money you make is considerably different, right? So in order to compare two interest rates, you look at something called the APY. And banks have to tell you this, right? So they might advertise an APR, but like in little print down the bottom, it should say there should be an APY, which is your annual percentage yield. How much money you are actually going to make. Sometimes it's called the effective rate, and APR is sometimes called the nominal rate, meaning in name only, and effective rate is how much you actually get. All right, so the APY is the percentage of profit that an investment generates in 1 year. So if you start with $1,000 and after 1 year you finish with $1,099.60, your APY is just the percent growth in 1 year. So percent change, remember from last class, is amount of change compared to original amount, right? So this account grew by $99.60. That's the amount it changed. And the original amount was $1,000. So my percent change, if I do this division, $99.60 divided by 1,000. And then that's a decimal, 0.0996, right? Which as a percent, you have to multiply by 100, move the decimal 2 to the right, and you get 9.96%. This is your APY on that investment. How much interest, what percent interest do you make in a year? So, okay, you guys try one. Compute APY on an account that begins with $835.25 and grows to $932.80 over the course of 1 year.